Okay, so this is the second part of section 9.8. And we are going to talk about using the calculator to do a few things. We talked about making a box plot from data, and we were doing example 7 last, and we made the box plot. We found the 5-number summary on male life expectancy in South Africa. And that data, the 5-number summary right here, I've entered into L1. We're going to make the box plot on our calculator here. The same 5-number summary that's been pre-made was made for females. You could enter all your data and it would do it for you. Or you can just enter your 5-number summary to look at your box plot. If they give you your 5-number summary, you can enter that. If not, I would just enter the data, and there's ways to find that, which I'll show you some of which coming up. But right now we're just going to do making a box plot. So to do that, I need to set up my stat plots. So I can get rid of those drawings now. So I'm going to turn plot 1, hit enter here. I'm going to turn plot 1 on. I'm going to go to this type, and I'm going to go to the box plot, not the modified box plot. It doesn't matter that much. My list here has got to be, we're going to do the males. Males I had in red. Red. There we go. And now we're going to set up plot 2, actually. So I can just scroll up here to the top and go to plot 2 and hit enter. And we're going to change this one to a box plot. And we'll do L2 now. This one I did in blue, so there we go. Red and blue. Now, pretty much anytime I'm doing this, I do zoom stat to start with. And I get this. Wow, that is X scale. How about 1, not 0.1? I don't know why it made such a small scale. Okay, so we can see the box plots here. Remember, red is males, females are blue. We can clearly see here that females on average live longer than males. Or different, or for have a higher life expectancy, I should say, which generally means they live longer on average. We can visually see this. I actually reversed the colors of what the book did, but that's okay. This is plotting it. Here's my box. This center line here is my median. That's median there. Q3 here. Max is the end of the whisker. Q1 and min. Everything is higher for the females. Higher minimum, higher Q1 is almost up at the median for the males. The median for females is above the max for males. So those are the important lines. You can use these to compare, okay? Side by side or stacked box plots are helpful and useful. Okay. Now we're going to go back to the whiteboard. We're going to talk about skewed data. Okay. Sometimes our data will be skewed a little bit one way or the other. So we usually like to view this off histograms. Here's going to be kind of a basic symmetric histogram. Now, this is not perfectly symmetric. Keep in mind that with these histograms, we are going a rough approximate shape. And that is roughly symmetric, okay? We can do another histogram that looks something like, hold on, I'll write this underneath. Symmetric. That is an approximate. Again, everything about these is approximating. This, you'll notice, has a tail off to the right. We'll do this like this. Long tail to the right. This is called skewed right. It is not where the high end is, it's where the tail is. This is skewed to the right, and then there's skewed left. So if they ask you the shape of a distribution, they're talking about it's going to be one of these three. Again, I'm doing histograms where we're approximating this. And this is about the direction of the tail. The skew is always in the direction of the tail. This is skewed left. Okay. Identifying an outlier. This is going to use box and whisker plots, and we're going to talk about the modified box plot. Okay? So we have some home runs totals, and we're going to talk about Roger Maris. Roger Maris held the home run record from the 60s until the late 90s with 61 home runs in a season. And his seasons ordered from least to greatest are 5, 8, 9, 13, 14, 16, 23, 26, 28, 33, 39, and 61. And now this looks a little bit like 61 might be an outlier. Doesn't quite fit. The rest of these have something sort of close by. So we're going to check. And I'm going to do the 5-number summary by hand, and we'll do all of this by hand. So my middle number, I'm going to put little markings. I'm going to do above so I don't cross them out. Find where the middle is. Okay, it's right here in the middle. It's halfway between the median is the average of 16 and 23. That's 19.5. Since my median is not included in either half, I'll do the two halves separately. The median is never included in these halves. So now let's do these with a red mark. Halfway between 9 and 13 is 11. Q1 here is 11. Q3, I can see it's going to be right here. Halfway between 28 and 33 is 30.5. The rest of my 5-number summary, min is 5, max is 61. So in order to find outliers, I need IQR. IQR is interquartile range. I do Q3 minus Q1. Interquartile range Q3 minus Q1. I shouldn't have made the 3 look like a subscript. We don't normally. I don't know why I guess I got used to subscripts. We don't normally make those subscripts. Q1, Q3. This is 19.5. Don't read into anything in any way that this is the same as the median. That's not normal. But it does happen on this occasion and sometimes. So I am going to do the definition of the IQR of outliers more than 1.5 times above the quartile 3 or below quartile 1. So we're going to calculate what's the upper, and we're going to make those, and we're going to call them upper fence and lower fence. The upper fence is Q3 plus 1.5. Why is it 1.5? That's the definition. Times IQR. Q3 is 30.5 plus 1.5 times 19.5. And this gives us 59.75. Okay. 61 is an outlier. It's further away. It's past, further from the middle from 59.75. The lower fence, same idea, but I'm now going out from Q1. So I'm subtracting 1.5 IQR. Which is 1.5 IQR is 29.25. So 11 minus 29.25. That is negative. This is not a meaningful fence. Negative 18.25. You cannot hit negative home runs. If it were possible, I would. But, I can't hit negative home runs. So the modified box plot, which is the one that's next to the box plot on the graph, makes outliers as points. Everything else about the box plot is the same. So my box goes from 11 to 30.5. The median line goes at 19.5. The min goes down to 5. The upper whisker is going to go to the highest non-outlier, which is 39. And then we place a dot for any outliers, 61. So that is the modified box plot for Roger Maris's home runs. Okay. So measures of center. There's two kind of popular ones. There is mean, X bar. There is median, M, capital M. There's measures of spread. These go together, okay? The standard deviation, and this is sigma, that stands for population standard deviation, is a measure of spread, and I'll talk about how to calculate that in a second. You can also have standard deviation is kind of the standard one. IQR is the measure of spread for median. Okay. If you're talking about medians, you use IQR for spread. If you're talking about means, you use standard deviation. There's also this thing called the variance, which is standard deviation squared. So it's just sigma, whatever value that is, squared. The formula for standard deviation, this gets a little ugly. I'm going to explain how you do it. First step in finding the standard deviation is to find the mean. And we're never going to calculate this by hand, this course. You do in some stats courses, but mostly you do it once and then you use a calculator. So the standard deviation is, oh yeah, we'll talk about the difference here, is you take each value, subtract it from the mean, you find how far each value is from the mean. Some of them are positive, some of them are negative. You just added all those up, you'll get 0. But if you take each value and square it, you get them all positive, and square all those values, divide by n, and then you square root. S here stands for sample standard deviation, which is slightly different. So technically mu, the Greek letter is population standard or population mean, X bar is sample. The Greek letters sigma goes with population. This standard deviation is only slightly different. Instead of dividing by the total number of numbers in the set, you divide by one less. Otherwise, everything about this is the same formula. So we're going to calculate this by hand. Example 10 gives us a bunch of data. And so we're going to put that all in the calculator. Please put it in your calculator with me. So I'm going to flip over to the calculator. And I'm going to go stat, edit, and go to my lists. I would do this, but I'm just going to do it. I'm going across the table in example 10. So I enter it. I didn't bother clearing because I know I've got way more data then. I am periodically checking. I know there's 8 or 10 across, so I'm checking that my numbers L1 that they match up with. It's L1 24, that this is the 24th term. Kind of checking that at the ends of the rows. Because I don't want to accidentally miss one. Okay, so now I've entered all my data. To calculate the standard deviation, we're going to go back to stat. We're going to scroll over to calc. One variable statistics is going to give us all sorts of things. We are using L1. We don't need a frequency list. Calculate it. Okay. Notice here, the bottom 5 things are my 5-number summary. Okay. That's kind of handy because it just gives it to you if you don't have it already. So you don't necessarily need to calculate stuff by hand. So at the top, they give you your mean, the sigma x is population standard deviation. Sample standard deviation SX, that's what we're often looking for. Wants the sample to estimate, 3.51 this is the answer I'm looking at, the SX. That is my standard deviation. That's telling me how spread out this data is. Okay. So finally, we're going to talk about a normal distribution, and that's where this standard deviation comes in. Sometimes called the normal curve, the Gaussian curve. Carl Friedrich Gauss, he's the one that had the formula from before. And he's kind of the one that invented this. So the beautiful thing about the normal curve. So this is the mean. So one standard deviation above. So my mean on that one was 88. We'll just say 88 and 3. So if this is 88, we're rounding those off very much. This is 91. Plus 3, this is minus 3, this is 85. This is 94. X bar plus 2 sample standard deviations, or plus 2 standard deviations and minus 2 standard deviations. So standard deviation is 3, X bar 88 minus 2 times 3 is 82. 79. Then we're going to do 3 standard deviations. And we'll call it 3 standard deviations away is between X bar minus 3X and X bar plus 3S. If this data is distributed normally, 99.7% of my data should be within 3 standard deviations. Approximately. Again, this is all approximate. If you have a lot of data, it's going to be real close. 95% should be between 2 standard deviations above and 2 below. That's between 82 and 94. And 68% here in this middle within 1 standard deviation. Yes, I can subdivide this. This is symmetric. That's 34% there, each side. I can take 95, cut it in half, minus 34, and get this to be 13.5. Out here, 99.7, that leaves 0.3% left, or 0.15% on each final tail. Again, this, if you have thousands of pieces of data, this really matters. So, based on the research, here's a little bit more exact. They want to know what's the top 2.5%. Well, if 95% are in the middle, it means I've got 5% out going on the wings. Split it in half, that's 2.5% each way. So my actual mean, and again, to do this, we're going to use the real ones, 87.49. And my sample standard deviation is 3.51. So I need greater than, any data point greater than the mean plus 2 standard deviations will be in the top 2.5%. And that is 94.51 grams. Anything above will be in the top 2.5%. The one we had in particular was 95. So that 95-gram loon chick is in the top 2.5%. Okay. That's a real quick introduction to statistics with the normal curve. And you can get more of this if you study statistics. That is the end of section 9.8.